Well, in the last video, I had said that when you have this the covariance structure, capital sigma theta, then all you have to care about when you are using it is how to specify that capital sigma of theta and leave to the computer the job of estimating the theta parameter by using maximum likelihood. Now, while that is in general true, there are two situations where you can use something simpler than just using the brute force MLE technique, and we are going to discuss them now. The first one is called generalized least squares or GLS. GLS, generalized least squares. This is not to be confused with something else which is called GLM, generalized linear model, that we will discuss later. So in this case, we have this setup. Capital sigma theta is of the form sigma square times some p. So sigma square is your unknown thing and p is a known thing. So unknown, and this is known and PD. So if your capital sigma theta is of this form, which means theta is just a single number, that is sigma square, then you can fit the model much more easily in the following way. So your model is y equals x beta plus epsilon, where epsilon has mean 0 and covariance matrix is. So what you will do is, you will take a square root of p. So since it is PD, you can write it as sum p to the power half, p to the power half, and I might say p to the power half, p to the power half transpose. So you can write it as something into its transpose, some non-singular matrix into its transpose, and I have denoted by p to the power half. There are various ways by which you can get this, and one way is by the so-called Cholesky decomposition. And this may be obtained in R using a function called Cholesky. It is not Cholesky but Cholesky. So if you use the Cholesky function of R in Cholesky P, then you will get this p to the power half. Now once you get such a thing, you pre-multiply the entire thing by its inverse. So p to the power minus half, so to speak, that is inverse of p to the power half, y, that is p to the power minus half x beta plus p to the power minus half epsilon. Remember, this is known, so you can consider this as your new design matrix. You can consider this as your new data and this as your new error. If I call it epsilon, then epsilon has mean 0. It had mean 0, you have pre-multiplied it with something, still mean 0. It had covariance this, so now it is sigma square p minus half p half, and that is just the identity thing. So now you have reduced it to our familiar Gauss-Markov setup, and you can just proceed. So in this case, you do not really have to write down the likelihood function and try to maximize. This is simple. Now, one special case of this where P will be a diagonal matrix with strictly positive known diagonal entries. So if P is like this, diagonal say W1 to Wn, then p to the power half is very easily computed. It is just square root of W1 to Wn, diagonal matrix with square root of W1 to square root of Wn. And in this case, sometimes it is called weighted least squares, WLS, when P is of this special form. At least our textbook calls it WLS, weighted least squares. Now you can possibly guess that this setup is a pretty contrived one, because why should you not know sigma squared yet you know what is the multiplier of sigma squared? So you may be using two different instruments to make the measurement. So you believe that the two instruments are possibly of two different levels of precision. So it is okay to say one set is sigma 1 square and the other set is sigma 2 square, but how are you ever going to know what is the ratio between them? So you can never express one of them as sigma square and the other as exactly twice sigma square. You do not know the level of precision, but somehow you know it is exactly double the level of precision as the other one. That is a pretty contrived situation. So this GLS thing is more like of theoretical interest. However, it occurs as an intermediate step of a more general thing that we are now going to discuss. When we want to perform a Newton-Raphson-like way of optimizing the likelihood or the log likelihood, then that is a pretty tricky operation, because you are making small little steps according to the direction along which the function will increase the most, and such an algorithm is generally very much sensitive to the choice of the initial value. So if you choose the initial value really close to the final optimizer, then you have good chance of converging to it, but if you start far away, you might not converge, or you might converge to some local maximum. So it is very important that you choose your initial value carefully. Now for that, we use a variant of this GLS technique, which is sort of very insensitive to the initial value. So you start from anything, and then this technique, which itself is an iterative one, the technique that I am going to describe now, will take you to more or less close to the correct value. After that, you will run your Newton-Raphson-like thing, the gradient-based thing, from that value to get to the final value. So the thing that I am going to discuss occurs in the first step of any Newton-Raphson-like technique. Now for this technique, we start with y equal to x beta plus epsilon, where epsilon has mean 0 and variance given by some particular structure. Now we assume that we have two things. Number one, we assume, so these are computational assumptions on basically the structure of capital sigma, this function. One, we can find Cholesky decomposition or some such square root decomposition analytically. So this is available. You really do not have to carry out any numerical technique to do this thing. Just looking at the structure, we can immediately say what is going to be the Cholesky decomposition. For example, if it is just a diagonal matrix, the Cholesky square root will be just taking square root of the diagonal entries. Now for all the techniques that you have learned, compound symmetry and then autoregressive one, etc., you can analytically compute such a square root. And the second thing is, if I give you some data, if I give you epsilon vector, something which has this, if I give you this, if is given, of course in practice it is not given, you are not observing epsilon, but if I give you a vector, then you can estimate theta. Then can estimate theta. So if these two assumptions are met, then there is a very simple way by which you can try to estimate this beta. And this technique that we are going to learn is called iteratedly reweighted least squares. Iteratedly, repeatedly reweighted least squares. And the technique goes like this. You first start with a guess for theta. So step 0. In step 0, you start with a guess. And this guess turns out to be quite unimportant. So you can just start with something which I call theta 0. Start with So this algorithm is pretty insensitive with respect to the choice of this, with some theta 0, some initial guess. Once you have that, you compute the Cholesky square root using this technique and you apply GLS. So now that you know theta naught, so you just assume that theta is known at this value. So now it is of the form. So typically we will assume it like this. So I will call it like this: epsilon is sigma square times some R. So R is the correlation matrix. So sigma square is unknown. So capital sigma theta I am taking up the form, this form, where I will possibly say this above R. That is a better way. Then can estimate sigma. Right, so then you can estimate theta, so that is okay. So start with some of this, and once you have this, now you are in a position where you can apply GLS. So step 1, apply GLS. And when you apply GLS, you will need to compute the Cholesky square root or some square root of R, which is analytically available. So you just put theta naught here, and if that does it. Once you have that, you get some estimate of beta hat. So to get beta naught hat, whatever you get, plug that to get your epsilon hat. Step 3, define epsilon hat 1 as y minus x beta hat naught. So now you get some estimate of some proxy values for epsilons. So I have assumed that if epsilons are given, then I can find out my theta. So you have applied GLS to get this as well as your sigma hat, sigma square hat. From GLS you can get that also. So now you go into step 4, which is basically you now get theta 1 hat. So use 2 to get theta hat, the next part, theta hat 1. So I will put there a 0 also. So now you get these values. And with this, you get back to step 1. So with this new value, you again apply GLS and you keep on doing this until you converge. So you keep on doing this until convergence. Is there any guarantee that it is going to converge? No, not always, but generally, if you do this, say some large number of times, not very large number of times, even 20-30 steps, you will see that you at least come more or less close to a very meaningful value of this theta, and from that point onwards you start your more rigorous Newton-Raphson method type of thing, and then the final thing converges. So whenever you are asking the computer to find out the MLE of beta and theta, what it will do is that it will start with some crude initial estimates and then initial estimate of theta, and then it will apply this for some 20 steps. Whatever it gets, it fits there as the initial value in the Newton-Raphson type iteration, which is much more sensitive to the initial value, and report the final convergence value. So, iteratively reweighted least squares. You understand why it is called iteratively reweighted, because I am using GLS every time, but I am changing that particular matrix. Because first I am working with R theta naught, then R theta 1, etc., etc. So I am iteratively reweighting it. And this is an important algorithm which generally sits inside your software. You do not have to do it, but something that we can understand easily.